Hey everyone, it's your friendly math teacher, Mr. Boyd. I'm back at it again today, and today I'm talking about U substitution. Previously, we talked about how to find integrals. Today we're going to learn a little bit more advanced technique for how to solve some more challenging problems, and that's exactly what a U sub is. So let's get started. What's the goal? Well, we're going to have some sort of nasty integral, something maybe like this, that has products in it, and it has rational functions in it. Now with derivatives, what we would do is we would find the rules that we needed. We would find in this case, we use a chain rule and a product rule. But with integrals, we don't have that. So what we're going to use is U substitution, and that's going to allow us to think backward and think about, well, where would this have come from? So here's what I do. I take all this nastiness, and I'm going to find an alternative way to write it. I'm going to change the variable. That's what U substitution is. We're going to change from x to u. Not u, but u. Okay? So what I'm going to do, and I'll explain how I did it in just a second, I'm going to decide I want u to be 4 minus x squared. All the stuff inside of there. I'm going to call that u. And I'm going to then take a derivative of u. That would be u du dx. And the derivative of that would be negative 2x. And the thing I want you to notice right away when I write that is that right here, that minus 2x is sitting there. That's good news. Now, we've got the minus 2x covered. So minus 2x matches right there, but there's also a dx right here. And so what I'm going to do is I'm going to multiply both sides of this by dx, so that cancels out. And now what I have written here and here is exactly what was in the original question. Okay? Now, how did I pick those? All I looked for is I looked at the original expression, and I looked for something that looks like a function and something like its derivative. It might not always match, but it'll be close. And so what I saw is right here, we had something squared. I know that when you take the derivative of something squared, you get something that's linear. So we had something squared, something linear. That must have been the u. That's du. Now here's what the substitution looks like. I'm tracking directly down from here. I'm just going to fill in these easier to work with puzzle pieces. So instead of 4 minus x squared, I'm going to write u. Because 4 minus x squared is u. And so now I have square root of u. Instead of negative 2x dx, negative 2x dx, I'm going to write du. And so this just got a whole lot easier to work with. Okay, we want to make it a little more calculusable. So let's change that form, u to the 1/2 du, and now we can integrate. And so we get u to the 3/2 divided by 3/2, or times 2/3. Don't forget the plus c. And then we have to make our substitution back, because this asked for an integral with respect to x, which means our final expression should be in terms of x. So I'm going to make that substitution back in, remembering that u was 4 minus x squared. So that would be 4 minus x squared. This says it's to the 3/2 power. It's multiplied by 2. It's divided by 3. And there's a plus c on the end. That's our first u sub. Okay, let's go on to the next one. We're going to do a couple of examples here, and we'll kind of try to pick up the pace as we go a little bit. Okay, so here's our second one, and what I want you to look for is something and its derivative, both of which are represented here. And so what I would want you to notice is that right there, there's an x cubed, and when you take a derivative of x cubed, you get something with an x squared in it, and we have something with an x squared in it right there. So what should you be? You should be the thing with an x cubed in it. We have to find du now. That's 3x squared dx. And this is where new students sometimes will start to have a little bit of heartburn around this, because that says 3x squared, and that does not say 3x squared. So now when we try to sub this stuff in there, it has the potential to cause some problems. So let's look at how we deal with those. So what I'm going to look at here, I'm going to rewrite my integral, and I'm going to start changing out everything I can. I'm not going to worry until I hit an issue. So let's start plugging it in. It looks like there's a fraction, and on the bottom there's a square root of a whole bunch of stuff. That stuff I defined to be u. I have an x squared dx, and so I absolutely want to keep the x squared dx. That would be good. That 3 is not where it's supposed to be, though. It's actually in the way. So all I'm going to do is the same thing we would have done back in algebra class. I'm going to divide both sides of this equation by 3. No big deal. Now it matches perfectly. X squared dx, x squared dx. So instead of x squared and dx, what I'm going to write is du over 3. Okay, And then what has to go right here? We need a placeholder. What placeholder do we always use in this situation? Always 1. Okay, and so I now want to rewrite this in a way that's a little bit easier to see. I'm going to box that off. And so the way I'm going to write that, I'm going to get rid of this in the numerator. I'm going to get rid of the radical. And so I'm going to write that as u to the negative 1/2. The other thing I'm going to do is I'm going to factor out my constant. I have, this right here is actually a 1/3 times du. So I'm going to bring the 1/3 to the front. I've still got a du out here, and now this is a fairly straightforward integral to deal with. We're going to add to the exponent, divide by that, so what I get is u to the 1/2 divided by 1/2 means times 2. Don't forget there's a 1/3. I'm going to write it like this, and then plus c. Of course, at the end, we have to resubstitute back in our x values, so let's do that. So I get 2 times square root of u, and actually I don't need those parentheses. Whether you choose to leave it as the 1/2 power or not makes absolutely no difference to me. If you're not one of my students, ask your teacher what they prefer. So I'm going to rewrite this as 2 times the square root, that's what the 1/2 power means, of course, square root of x cubed plus 1 over 3 plus c. Alright, now we'll get into ones that have little tricks to them and are just a touch more advanced. Okay, so a lot of new students, when they look at this, they get a little bit panicked because they look for something and its derivative. And it looks like we have root x in 2 places. Well, root x is not its own derivative, and so we get a little panicked. I think I can write this in a different form. Don't forget your dx. I think I can write this in a different form that might be a little bit easier to interpret. So what if I write it as sine of x to the 1/2 multiplied by x to the negative 1/2. All I'm doing is I'm bringing that up to the numerator. I hope now what you can see is if you subtracted 1 from that exponent, think the old power rule, then you would get something that looks very, very similar to that. And so what that indicates to us is that u should be x to the 1/2. Now when I first started learning these, I would always put sine of x to the 1/2. I would bring that with me. So let's talk about why that's wrong. If you pick sine to be part of your u, what happens when you take a derivative? You're going to end up with a cosine in your du. And there's no cosines here. And so we'd have nowhere to plug that in. Now that can happen. Sometimes you're going to pick the wrong u the first time. That's okay. Okay, find what du is. See, is there a way to plug this in? If there's not, that's a pretty good indicator that you might have the wrong u value chosen. So you just back out and you try a different value of u. Okay, this is going to be the correct value of u. So du equals 1/2 x to the negative 1/2 dx. Let me box that off. Let's make a substitution. Okay, so I've still got my integral, sine of u, and then I've got an x to the negative 1/2 dx, I've got an x to the negative 1/2 dx right there, that's fine, but there's a 2 in the way, or a 1/2, so let's multiply by 2 to cancel it out. So instead of x to the negative 1/2 dx, I have to write a 2 du. Now you can totally put the 2 in here, but why would you? Okay, it's just multiplied. Remember, this is commutative. The order doesn't matter so long as we're talking about multiplication. So you can factor out that 2. Not a problem. In fact, it's going to make it easier. Okay, let's keep going. We know the integral of sine is negative cosine, so we get 2, or negative 2 cosine u du. Oh, excuse me, not du. I got confused for a second. It's actually plus c, because we've actually done the integral now. So plus c, and then that turns into negative cosine, not u. U was x to the 1/2. I'm going to change it back to the original form just because that's what I like to do. So I'm going to get root x in there plus c. Hopefully by now you're getting to the point where you feel comfortable pausing the video, trying to at least pick u by yourself and see how you did. I'd encourage you to pause the video and try going through the whole exercise by yourself. So when you're ready, hit unpause. This is how it goes. Okay, for this one, I'm going to pick u to be that exponent, x squared plus 2x plus 3. Du then is going to be 2x plus 2 dx, and that makes the substitution pretty simple. Because 2x plus 2 dx, let's pick a different color, 2x plus 2 dx matches that perfectly. If that helps you, color code it on your page. Get 2 different color pens so you can see what goes where so these puzzle pieces match up. And then I've got my u right there, and so everything except the e is accounted for. That's great because we know how to take integrals of e, so it's not a problem. Okay, so let's fill it in. So instead of 2x plus 2 dx, I just get du. Oh, that is so nice. All that stuff went away. And then we've got an e to the u. How do you integrate e to the u? It's its own derivative. So what we get then is e to the u plus c, plug our x back in, or our u back in, excuse me, and so we get e to the x squared plus 2x plus 3 plus c. Okay, and that's our solution. Now, if you're wondering, what the heck are we doing? Why are we doing that? We're finding an integral, and we can test to see if we're right by taking a derivative. Now, the prompt didn't ask for it, but I'm going to show you what happens if you take a derivative of this. Now, remember your e rules. It says, write what you see, e to the x squared plus 2x plus 3. Down in front, we write the derivative of the exponent. Exponent's right there, so that would be 2x plus 2. And then we've got this over here, derivative of a constant is 0. Isn't that the exact thing we started with? Let's check. Yeah, it is. That's exactly what we started with up there. So what does that tell us? We integrated. Integrals and derivatives are inverses, so if we do an integral and then a derivative, we should get back what we started with, and we did. So that verifies that we did this correctly. Okay? Now I think you definitely can pause the video and try this one on your own. If you're ready to go for it, unpause, here we go. U equals x cubed plus 3x. Du equals 3x squared plus 3 dx. And when we start subbing, we run into a little bit of an issue. Our denominator matches perfectly, so we get something over u. But we have x squared plus 1 dx, and this says 3x squared plus 3 dx. It's too big. There's a simple trick for that. Divide by 3. And then we get du over 3 equals x squared plus 1 dx. And notice that right there matches perfectly. Okay? And so off we go. So now to make that substitution, instead of writing all that stuff, I'm going to write du over 3. And notice how I wrote it strategically so I don't have to do extra steps. I could have written du over 3, or I could have written du over 3 up there. But that makes it harder for me to see what's going to happen. And so I've written the 1/3 out there. I need a placeholder right there. And so now I'm good. Now you'll have to remember that when you have a form like this, 1 over a variable, that came from a natural log. So this is 1/3 natural log absolute value of u plus c. Let's make the substitution backward and we'll be done. Bring my equal signs over. Okay, and so I get natural log of x cubed plus 3x plus c. Now do you see where I've made a mistake? Okay, there's a mistake in my answer. Look carefully for it. Pause the video if you need to, because spoiler alert, here it comes. I forgot to bring this 1/3 over. Okay, so be careful, make sure you don't make those mistakes. They do happen though. Okay, we're done. Alright, so now we're going to get into part 2. Part 2 is where we start to put bounds on them, okay? So we have definite integrals now. And so it's not harder, there's just one little trick that happens. If we can get that one little trick down, these are a total piece of cake. Okay, let's get it. Okay, so here's what we do. We start the exact same way we've done in the last 4 examples. We pick our u, and we integrate. So for me, looks like x minus 1 is going to be my u, and then my du is 1 dx, so it's just dx. So that's going to make this substitution really, really easy. And so I get u to the 25th. That looks pretty good. The dx turns into a du. And here's what brand new students often do. They'll just say, oh, it's 0 and 2. Pause. Okay, here's the issue. Is that 0 an x value, a y value, or something different? Okay, well, it's an x value. Okay, so that's x equals 0, and that's x equals 2. The reason we're not writing x equals is because it's already implied. We have a function in terms of x, we're taking an integral with respect to x, and therefore the bounds are in x. Now down here, same thing, you've got u and u, so now you're saying those are u values, but they're not. And so one thing you can do, you could write x equals here, but that's a little bit cumbersome, and so let's look at the easier way to do it. If we want to turn those into, and when I say those, I mean our original bounds, 0 and 2, I want to turn those into u values. The easiest way to do that is to use this equation right here that we have for u. And so that's what I'm going to do. I'm going to plug those in. If I plug in a 0 right here, 0 minus 1 is negative 1. If I plug in a 2 right here, 2 minus 1 is 1. And now we have u values. Now what that's going to allow us to do is we're not going to have to switch back into x's anymore. We're going to be able to answer this question because since it's a definite integral, our answer is going to be a number. This will allow us to get that number. Enough talk, let's do it. Okay, so what we get is u to the 26th over 26, bounds from negative 1 to 1. Here we go. When you plug a 1 in there, it's like 1 to the 26th is 1, divided by 26 is 1 26th. Plug in a negative 1, even exponents make it go positive, and so I get 1 over 26. So out pops 0. We found the solution to our definite integral. A couple more. Let's try this one. If you're ready to pause the video, go for it. If you're not feeling great yet, then follow along with me. We still have to pick what u is, so I'm going to so I need to let u equal 3 minus 5x. du equals negative 5x. Oh, excuse me, not the x. I was thinking of dx. Negative 5 dx. There we go. That's better. And so now I'm ready to make a substitution, or at least to start thinking about a substitution. Okay, so what I'm going to do, I've got my u down here, so I'm going to write it as u to the negative 2. I'm going to bring it up to the numerator. It's going to make it a little bit easier in just a minute. And then I've got my dx to deal with. I've already dealt with that. I've got a dx, but there's a negative 5 next to mine. So let's divide out the negative 5. So instead of dx, yes, I'm going to put a du, but I need a 5 in a denominator. I'm going to write it like this. And now that's all set. Okay, we need to get our bounds. So plug in a 1 over here. 3 minus 5 times 1, I think that's negative 2. And 3 minus 5 times 2, okay, 5 times 2 is 10, so 3 minus 10 is negative 7. And away we go. Okay, so from this I get u to the negative 1 over negative 1. I've still got the 1/5 right there. And don't forget your bounds. Cool. So I probably need parentheses around that. And to my eyes, that looks a little bit confusing. I'm going to try to simplify it out a little bit. And so when I combine these together, I get negative, no, redo. Looks like I get a negative 1 over 5u. Still have my bounds, negative 2, negative 7. So let's apply the fundamental theorem and let's try to get a solution out of this. Okay, so what I get negative 1 over 5 times negative 7 minus negative 1 over 5 times negative 2. Okay, let's try to simplify down just a little bit. So it looks like I got a negative and a negative. That's going to go positive. Seems like I have 1 over 35 over there. Now we've got negative, negative, negative. 3 negatives. Leave it as a negative. Minus 1 over 10. Okay, let's get our common denominator. That looks like that's going to be 70 in this case. So 2 out of 70 minus 7 out of 70. And we get negative 5 over 70. Alright, we should probably simplify that down too. Okay, so let's see what we get when we divide top and bottom by 5. I get a negative 1 on top. What about on the bottom? Looks like it's probably 14. So there we go. Alright, and now for some more fun. Okay, with this one, people get a little frustrated because they see x and they see x, and x is not its own derivative. But again, if you're not sure, just try something. Now the trick on this one is if you start out with u being the natural log of x, and remember that the derivative of that is 1 over x dx, you see how this actually is a 1 over x and a dx? Now it matches. Okay, so let's do it. So in terms of, or instead of natural log, I write u. I have a 1 over x dx right there, and so that's going to be du. Don't forget to change your bounds. Plug in a 1 right there. Natural log of 1 is 0. Plug in an e. Natural log of e is 1. And that nasty problem just got pretty darn easy, so let's do it. I get u squared over 2, bounds from 1 to 0. Looks like that would be 1 squared over 2 minus 0 squared over 2, which is just 1/2. Okay, and this is going to be our final one. For this one, see I've got x squared and then I have something linear, so that indicates to me there's a really good chance that my u is going to be x squared and du is going to be 2x dx. So let's go for it. Alright, I've still got the cosine in there. And now it's going to be cosine of u. That's good, we know how to deal with that. I have an x dx right here, which matches the x and the dx, but there's a 2 in the way. So let's divide it out. Okay, there it goes. And so now I have a 1/2 and a du. Let's get some new bounds. So plugging these in, if I plug in a 0 into x squared, still get 0. If I plug in root of pi into x squared, hey, that square cancels out the root. That's nice, that just got a little easier. Okay, now I've got pi up there. Make sure you know that's a 0, not a 6. Okay, so now I can integrate this. And so I get 1/2 cosine turns into sine, so half of sine of u with bounds 0 to pi. Psh, no big deal. Okay, let's do this. So I get 1/2 of sine of pi. Okay, what is sine of pi? Pi is over there, so that's 0. Minus sine of 0. Okay, 0 is over there. Sine of 0 is 0. Half of 0 minus 0 equals 0. I always like to make a little face out of these two just for funsies. Okay, now we got a little guy there. Still, it equals 0. Okay, so that's 8 examples on U subs. Hopefully that's enough to get you going, to get some practice, and to get feeling really, really comfortable. Until next time, have fun. I'll see you then.